Okay, so let us now have this sample problem for torsion reinforcement. So in this situation, a beam is subjected to gravity loads that cause torsion due to cantilever beams attached to it. So from the analysis, it was found out that at a critical section near the face of support, the beam experiences an ultimate shear of 264.54 kilonewtons and an ultimate torsion of 64 kilonewton meter at the exact same location. So take note that these magnitudes here are already the ultimate shear. So when we say ultimate shear, that these are already factored. Okay? So during the design of the rectangular beam in bending, the beam was designed using a breadth or width of 450 millimeters and a total depth of 550 millimeters. So the concrete cover that we will be using is 40 mm and only one layer of 20 mm rebars will be used for the tension bars. So for our parameters, we would now be making use of a compressive strength of concrete equal to 21 megapascals. The yield stress or the strength of the main bars as 420 megapascal, and the strength of our transverse bars equal to 280 megapascal. So for the closed loop stirrups, so again, this will now be our transverse bars. It will now become, or it will now be closed loop stirrups, and we will now be making use of 12 mm diameter rebars. So in this problem, we will now be designing the spacing of stirrups if closed loop stirrups will be used. Okay, so first things first. So I have already summarized the given here. So we have VU, TU up until DV. So as you can see that in the parameters, we do not have the effective depth. So if you are thinking that the effective depth is already 550, so you are mistaken there. Since this is the total depth, meaning by total depth, it is measured from the top up until the bottom. So my approach here is that I will be solving first the spacing of the shear reinforcement. Then if I have already solved for the shear reinforcement, I would now solve for the required spacing for torsion reinforcement. Then I will be getting the resultant, so to speak. Okay, so my first step once again is for me to solve for the shear reinforcement using simplified method first, but I will be fast here since this is not the main focus of our video. So I hope that you can get along with my pacing here, and if not, better pause the video, replay it, or better yet, just watch the previous video lecture that I have already uploaded on the design of shear reinforcement. Okay, so in the design of shear reinforcement, we actually need the value of D. So for the value of D, that is basically equal to H, which is 550, minus the concrete cover, minus the shear stirrups, which is 12 mm, minus half of D, or half of dB. So that is 20 over 2. So again, this is only one layer as per indicated in the previous slide. So getting the difference here, we would now be getting a total, we will now be getting an effective depth of 488 mm. Again, since we are solving for the shear reinforcement, so since in our design principle before, VU is equal to phi Vn, but Vn is equal to Vc minus Vs. So this is now our formula, or the formula that we will be making use. So we already know the value of VU, and we are actually solving for the value of Vs in order for us to know what the spacing is. So from that, guys, cross-multiplying this or isolating Vs to one side, Vs is now equal to VU over phi minus Vc. So this equation came from this equation. So since we already know the value of VU, we should solve for the value of V sub C using simplified method. Okay? So proceeding, Vc is equal to 0.17 times lambda times square root of f prime c times bwd. So substituting all known values, 0.17 times 1 times square root of 21 times 450 times 488. So giving us an answer of 171,076.7 newtons. So once again, I am not really calculating here using our calculator. I have already pre-solved for this in order for us to get this over with. So in order for us to get over this solution, since this is not really the main focus of our video. Okay, so for VC, we have found out that it is 171,076.7 newtons. But once again, this is not what we need. What we need is the value of Vs. So moving forward, for Vs, substituting all known values to this particular equation, whereas Vs is equal to Vu over phi minus Vc. So upon substitution and upon solving, the answer for Vs is now equal to 181,643.28 newtons. So meaning that this is now the shear force that the stirrups would be carrying. And from this Vs, we can now solve for its required spacing. And the required spacing is equal to AV times FYT times D divided by Vs. So substituting all known values, so take note that for our AV, we are now to make use of closed loop, meaning that we have two legs, okay? So for AV, that is now 2 times pi over 4 times 12 squared. So since we have two legs, times 280, that is FYT, times D, so take note. So I have a typographical error here. Let me just correct that. So that should be, so not 500, but rather that should be 488. So let me edit that. 488. Okay. So again, let us go to that slide once again. So that is, that should be 488. So getting the answer there, we would be arriving at an answer of 156.9 millimeters. And since this number here is kind of irrational if we would be indicating that to our design, it would be better if we would be rounding them up, or I should say we would be rounding them down. So we are rounding them down in order for us to have a safe structure. So upon rounding them down, I have decided that I will be making use of 150 mm. So for 150 mm, that is now our S required, but we are not yet done there. We should know first what the value of S max is in order for us to know if we would now be making use of this or S max. So for the maximum spacing, again, our limit is 0.33 lambda times square root of F prime CBWD. And upon substitution of all of these values, this is now equal to 0.33 times square root of 21 times 450 times 488, and getting the answer there, that is now equal to 340256.2 newtons. Okay, so this is now our limit, and as you can see that this is our Vs, which is 181,643.28. And since this Vs is less than this limit, so again, Vs is less than our limit, and thus, for our S max, we will now be making use of this table since our Vs is less than 0.33 square root of F prime CBWD. So it is now the lesser of D over 2 and 600. So for D over 2, so D over 2, that is equal to, once again, our D is 488 divided by 2. So this is now 244. Okay? So between 244 and 600, we now know that 244 is the lesser value, and from that, our S max is equal to 244. So from that, guys, the value of S required will govern since it is less than our S max. Okay, so this is just for shear. So for the torsion, so let us now proceed to the torsion reinforcement. Okay, so for the torsion reinforcement, once again, the first thing that we should do is for us to check if it is really needed. And in order for us to know if it is really needed, we must solve for the threshold torsion first. So for the value of TTH, once again, that is equal to 0.083 times lambda times the square root of F prime C times ACP squared divided by PCP. Okay, so let us solve for ACP and PCP first. So for ACP, this is the area of the outermost section of the beam. So meaning that all of this, okay? So let me just erase that. So ACP, so take note that this is 450 mm and the entirety of the depth is equal to 550 mm. Okay? So this is 450 mm and this is 550 mm. So looking at the calculator to your left, so 450 times 550, that is now equal to 247,500. So again, this is 450 times 550. So again, this is 247,500 millimeter squared. So for the value for PCP, we were just getting the perimeter of the beam. So, sorry. So from that, that is now 450 times 2 plus 550 times 2. So from that, the PCP is now equal to, so looking at the calculator once again, so that is now 450 times 2 plus 550 times 2. So the answer here is 2,000. Then substituting all known values. So TTH is now equal to 0.083 times 1 times square root of 21 times 247,500 squared divided by 2,000. This is now equal to, so looking once again to the calculator to your left, so substituting all known values, 0.083 times square root of 21 times 247,500 squared divided by 2,000. So this is now equal to 116,49523.2. So the units here is, or are, newtons millimeter. So as you can see that since we have used megapascal here, or Newton millimeter squared, and this one here is millimeter squared, but take note that this was also squared once again, and this is in millimeters. So unit analysis, you would be left with unit of Newton and millimeters. So if you want to convert that into kilonewton meter, just divide that by 1 million. So just divide this by 1 million, or times 10 raised to negative 6. So our threshold moment, or threshold torsion, is equal to 11.649 kilonewton meter. So as you can see that our torsion is 64 kilonewton meter, and the threshold is 11.649. So from that, as you can see that since our required torsion is 64 and our threshold is less than that, it means that torsion reinforcement is required. Okay, so once again, since the value of our torsion is greater than TH, or actually we should still be multiplying it, but it is kind of common sense already that it is, this is now the case. So TU is now greater than phi TTH, and our torsion is once again 64 kilonewton meter, and this is actually greater than 0.75 times TTH, and TTH is once again 11.649. So 11.649. So without me even solving for this, I know for a fact that this is greater, and from that, torsion reinforcement is required. So again, required. Okay. Okay, so in order for us to check if the section dimensions are adequate, we should now check this equation if it would be satisfied. Okay, so as you can see that in this equation, we need the value for VU. We already have that actually. We also know, we should also know the value of TU, PH, AOH, and etc. So the only new parameters here are the values for PH and OH. So for those values, we would once again shade the area of concern here, which is bounded by the middle of the shear reinforcement, or of the stirrup. So from that, guys, as you can see that this is now to be it. So let me just zoom in here. So as you can see, only half. Okay, so only half of the stirrups were occupied. Okay, so as you know that for the entirety of the beam width, or the beam breadth, that is equal to 450 mm. And on both sides, we would be having two concrete covers. Then aside from the concrete cover, we would now be subtracting once again half of the diameter of shear stirrups at both ends. So from that, this particular dimension here is now equal to, so 450 mm minus twice the concrete cover minus twice half of the stirrups times 2. Okay? So from that, looking at the calculator, the dimensions there would be, so 450 minus 2 times 40 minus 2 times 12 divided by 2. So our answer here is 358 mm. Okay. So that is for this dimension. But what about for the vertical dimension? So for the vertical dimension, the total depth, once again, is 550 mm, which is this one here. So 550 mm minus, we also have 2 concrete covers here. So minus 2 times 40 minus, so twice the half of the shear stirrups or the shear reinforcement. And the answer here would now be equal to, so looking once again at the calculator to your left, so 550 minus 2 times 40 minus 2 times 12 over 2. Answer here is 458. Okay? So 458 mm. So for the value of AOH, that is equal to 358 times 458. And for the value of POH, or PH I should say, that is now equal to twice 358 plus twice 458. So once again, this is just the perimeter. So our answers here respectively are, so looking once again at the calculator, so 358 times 458, answer 163,964. Then for the value for pH, that is once again 358 plus 458. I would just be multiplying this by 2. So 1632. So substituting all known values to our equation on the left, so VU is equal to 26.54. But take note that in order for us to have unit consistency, let us convert this into newtons first. So 26540 newtons divided by 450 times 488. Take note that this is D, not H. Plus TU, and our TU is 64 kilonewton meter. But take note once again that this must be, oops, sorry, my mistakes. So this must be multiplied by times 10 raised to 6 in order for us to convert it into Newton millimeter. So once again, this is 64,000. So times 10 raised to 3 once again. Or 64 million, I should say. So times 1632, that is 1632 here, divided by 163,964 squared. And this must be less than this equation on the right. Okay, so in order for us to confirm, using my calculator, so 264,540 divided by 450 times 488 quantity squared plus, plus 64123 times 1632 divided by 1.7 times 163,964 squared. Okay. So my answer here would be 1.933. Okay. So the answer here on the left is 1.933. And for the one on the right, so take note, our answer is 1.933. And for the one on the right, this is 0.75 times the quantity of 171,076.7 divided by 450 times 488 plus 0.66 times square root of 21. So that is 2.85. So in summary, 1.933 is less than or equal to 2.853. So meaning, guys, that for our cross-sectional, it is adequate. Okay? So cross-section, check. Okay. So next up, let us now solve for the spacing required. So once again, since VU is greater than not VU. So since TU, I should say, since TU is greater than T TH. Let us solve for the shear reinforcement. And earlier, I have indicated, or I have told you the solution for Vn. So Tn, I should say once again, Tn is equal to 2AO times 80, so this one here, times Fyt divided by S. And take note that cotangent theta is already equal to 1 since theta is equal to 45 degrees for non-pre-stressed. So to prove it to you that cotangent is equal to 1, so cotangent is actually equal to 1 over tangent, or the inverse of tangent. And for non-pre-stressed members, the angle there is 45 degrees. So 45 equal sign or equals 1. Okay? So from that, for our solution here, for the value for Tn, where will I write? So for the value of Tn, this is equal to 2, again, 80. So 280 times, what is the equation once again? So 2 times 80 times AO times Fyt divided by S. Okay? So 2 times 80 times AO times Fyt divided by S. So again, for cotangent theta, we do not need to include this any longer since this is already equal to 1. So again, it came from this equation. So 2AO 80 Fyt S. So for the value of 80, this is just the area of one leg for the stirrups itself. So once again, this is the stirrups. So again, for one leg, that is pi over 4 times 12 squared. So that is already the value of 80. So for AO, it is indicated earlier that in our analysis, it is permitted by NSCP that the value that we will be making use for AO is equal to 0.85 or 85% of AOH. And this is now equal to 0.85 of what is now AOH. We have actually solved for it earlier already. AOH is 163,964. So 163,964. Okay. So from that, guys, what we will be doing is that we will be solving for Tn in order for us to solve for the value of S. So for the value of Tn, so take note that Tu is equal to phi Tn. And from that, from this equation, Tn is now equal to Tu over phi. And from our problem, we have indicated, or it is indicated in the problem, that the value of Tu is equal to 64 kilonewton meter in here. Okay? So, that is 64 kilonewton meter. Let us multiply it by 1 million in order for us to convert it into Newton millimeters, in order for us to have unit consistency. So, divided by phi of 0.75. So, our answer here is now equal to, so 64 million divided by 0.75. Oops, sorry. Divided by 0.75. So that is now equal to 8533. So how many threes are there? So 333, 333.33. Okay, so that is now the value for our Tn. So from that, guys, once again, Tn is equal to 85333.33. And since from our earlier equation, this is now our governing equation. So 85333.33 is equal to twice AV, and AV, I mean 80, I should say. So 80 is equal to pi over 4 times 12 squared. So this is just the area of one leg. Times AO, and AO is 85% of AOH. So what was our AOH once again? That is 163,964. So 163,964. So there. So times FYT, and according to the problem, that is FYT is 280 megapascal. So 280. So divided by S. Okay, so from that, the required spacing for torsion is now equal to, so looking at the calculator, you can either make use of shift solve, or better yet, just transpose or just cross multiply. So once again, 2 times pi over 4 times 12 squared times 0.85 times 163,964 times 280 divided by 853,333,333.33. So from that, the spacing required for the torsion is equal to 103.44 millimeters. So take note, guys, that in order for us to have, let's say, a rather sufficient section, or let's say a rather realistic spacing, I should say, we can actually use 100 mm here. Okay? So now, as you can see, that for our spacing for torsion, we have used 100 mm. So once again, this is for torsion. And earlier, we have also solved for a spacing of, where was that again? So a spacing of, what is your spacing? So the spacing for shear equal to 150 mm. This was earlier. So 150 mm. So looking at our spacing, so again, 150 mm. This is for shear. So if you are thinking that we should just use 100 mm, since this is the lesser value, then I'm sorry to tell you that you are mistaken in that. So according to our what you call this? According to our, where is our code provision? So according to our code provision, you must be adding them, or you must be taking both into consideration. So take note that according to our provision here, the transverse reinforcement required for torsion shall be added. So we will not be choosing the more conservative value, but rather we would be adding them. But since we are talking about spacing, guys, it would be incorrect if we would just be adding both of this. So meaning that we will not be adding 100 mm and 150 mm. Since if we would be adding them, the spacing is now equal to 250 mm. Rather, we would now be getting its kind of the inverse average of sorts. Okay, so what I would be doing here is that, let's say that this is now the total area for both shear and torsional bars, and I will be dividing this by the governing S. Okay, so this is now equal to the area for the shear bars divided by the S for shears plus 2 times A of T, or the area for torsion, divided by the spacing for torsion. So once again, this is for SV, and this is now for ST, or so this one here is for ST. Okay, so take note that this is only true for 2 legs. So if you want to change the number of legs, just change this number here. Okay, anyway, so substituting all known values for the value of AV plus T, so it would be up to you. Okay, so for the value of AV plus T, since in my design I will only make use of 2 legs here. So as you can see, we only have 2 legs here. So meaning that I will be multiplying this by 2 times pi over 4 times 12 squared. So if you are thinking that this is for the number of legs for AV, this is 2. Then for the torsion bars, this is 1. If you are thinking that shouldn't it be 3, then you are mistaken, no? Because at the end of the day, you will only make use of 2 legs for the combination of both of them. Okay? So the only thing that would differ here is the spacing itself. Okay? So again, we will still be making use of 2 here. divided by the governing S. Okay? Okay. So this is now equal to AV. So AV, we would now be having 2 legs of 12 squared divided by SV. SV is, according to our computation earlier, that is 150 mm plus 2. So 2 times pi over 4 times 12 squared divided by, according to torsion, that is now 100 mm. So I will now be making use of shift solve for my solution here. So looking at the calculator to your left. So 2 times pi over 4 times 12 squared divided by alpha x. This is now equal to 2 times pi over 4 times 12 squared divided by 150 plus 2 times pi over 4 times 12 squared divided by 100. So getting the answer here, shift solve. Our answer is now equal to, so S is now equal to 60 mm. So this is now the spacing that we will be using. So not 100, not 150, but 60 mm. So this spacing here now resists torsion, or both torsion and then shear. Okay? So next up, let us now check if that is within the limit for AV min. Okay? Okay, once again, let us solve for the AV min if it is within our standard, or if it is within the standard. So for these equations here, so according to NSCP, these equations here are AV minimum divided by spacing. Okay? Once again, this is AV min divided by S. So we will now be choosing whichever is greater. So since we would be solving for AV min, let us just cross multiply this and put spacing to the other side. So what I mean here is that let us now include S here on the right side of the equation by cross multiplication. Okay? So there. Okay, so substituting all known values, this is now equal to 0.062 times the square root of 21 times 450 divided by 280 times the spacing that we have computed earlier is 60. Okay? So this is now equal to, looking at the calculator to your left, 0.062 times square root of 21 times 450 divided by 280 times 60. So this is now AV minimum, which is 27.398 millimeters squared. That is for the other one. And as for this one here, this is now 0.35 times BW of 450 divided by 280 times S, and the spacing that we have solved for earlier once again is 60 mm. So from that, guys, this is now equal to 0.35 times BW of 450 divided by 280 times 60. So the answer here is now equal to 33.75. And as you can see, the greater between the two is this. So basically, this is now our AV minimum. So for our AV actual, or actual AV is now equal to, so since we have used 2 legs, so 2 times pi over 4 times 12 squared. So this is now equal to, looking at the calculator, so 2 times pi all over 4 times 12 squared. So our answer here is 226. So 226.195, which is of course greater than AV min. Okay? So this checks the box. So that is how you would be designing stirrups in torsion. So there.